So thank you. First of all, I want to say thank you very much for organizers for the possibility to discuss this work in this conference. And second, I want to say thank you very much for all participants. I can see here real experts in very high cyclic fatigue. So I try to be fast, and I can see a lot of experts. It is allow me to skip the beginning of my presentation. I don't speak a lot about duplex Wöhler curve, about peculiarities of crack initiation and the gigacyclic fatigue, and just I will show our experimental results and our attempts to describe the damage to fracture transition under very high cyclic fatigue. In the beginning of this presentation, I have to describe the origin of this presentation. The presentation was initiated by our collaboration with Italian team from University Messina, and it can be considered as a first step in this collaboration. The Italian guys have very good experience in thermography, in application of thermography to ultrasonic fatigue, and we try to find some equation which can describe the temperature evolution under gigacyclic fatigue. When I say temperature evolution, I mean energy balance in the sample, and we do a lot to study energy balance under different kind of loading, under dynamic loading, under cyclic loading, and even under gigacyclic loading. So, next slide presents the outline of my presentation. I can skip first peculiarities, second ELSA. I will say several words about our structural investigation. I will repeat a little bit our previous results and try to show some new results which can be answered on the question which appear on the last crack path conference. We did some structural investigation with titanium. And after, I will say several words about statistical description of defect and sample which was developed in our institute by Professor Nymark, and how we can use this statistic to find the phenomenological equation which describes the energy balance in the metal under defect, under damage accumulation. And I will finish by preliminary results. So it's just an idea where we are from. It is a PERM, it is a Russia, and it is a number of laboratories in our institutes, and red marks stress the laboratories which working with infrared thermography. So we are working with it, and we have some experience, and I think it's very good collaboration. So I skip this duplex Wöhler curve, the description of this curve, fissure initiation, the model of crack initiation and the gigacyclic fatigue. But just one thing what I want to keep in mind. We have at least two regions of crack propagation. This one, it is an ordinary crack propagation, and we can simulate the energy dissipation and the crack propagation in the Paris region. But the formation of optical dark area, of fine-grained area, it is still open question. In the excellent lecture of Professor Honk, which opened this conference, he presented several models of optical dark area initiation. But it's, up to now, as I know, it's a quantitative model. The people try to describe the mechanism and just go to the mathematical equation. We can go from another direction. We try to find a mathematical equation which can describe the initiation of optical dark area, and after to find the structural mechanism. A little bit different way, but maybe it also would be just so. I skip it also, and I try to repeat our previous results. What we have done, we have carried out the experiment with Arca iron loaded in very high cyclic fatigue. We took 5 samples with different lifetime and investigate the dilatation evolution in these samples and decrease and degradation of mechanical properties, elastic modulus, logarithmic decay, and dilatation. This work was made in collaboration with our colleagues from St. Petersburg. And the results is very interesting from my point of view. For Arca iron, it's very clear and bright. We have 2 ways of sample polishing. We take a sample from the specimen loaded under gigacyclic fatigue and change the diameter of samples and change the length of samples. And each step we measure the density of these samples. As a result, we have shown that under gigacyclic fatigue we can take increasing of dilatation and maximum of this dilatation just in the middle part of the sample. I show only one slide. This result was presented in the previous conference and it was published in our papers. But next step, we are going to the titanium alloys, and we was working with nanocrystalline titanium, and we also measure the influence of gigacyclic fatigue on the dilatation and the mechanical properties. Here you can see the properties of titanium before very high cyclic loading and after very high cyclic loading. What does it mean after? It's not cracked sample, but it was loaded more than 10 in power 9 cycles. What we can see changing in density. Not very high, but the procedure is very sensitive and each digit is real digit. So we have increasing of dilatation and we have changing in the mechanical properties. Young modulus also decreasing, and it means we have some initiation in this samples. If we take into account dilatation, we will write the model just for the media with some defects which have bulk mode. Or what should we do if we want to write the model like this? I told you that we are going to write to describe the energy balance. We have to start from the energy balance equation, take into account second thermodynamics law, and the main question is how we can write the thermodynamic potential of this system. From this point of view, I can speak a lot, and it's not enough time to describe it in detail. There are different approaches to find the thermodynamic potential, to introduce new thermodynamic variables. But if we are following, for example, if we are following the paper by Razakis, we can show that thermodynamic potential of a system can be written as a sum of three items. First one is ordinary, and second one is a structural sensitive parameters. And the main advantage how we can introduce these parameters. And in this situation we can use the approach which was proposed, as I told, by Professor Naimak in our institute, a little bit developed for cyclic loading, but up to now I want to finish the general energetical part of this equation. If we write energy balance, do some mathematical manipulation, we can update the thermoconductivity equation with two parameters, thermoelastic effect and thermoplastic effect. Thermoelastic is quite simple, but thermoplastic requires the determination of structural sensitive parameter. How it's possible to do? And one of the possible, if we have such equation, we can write this. Equation for calculation of stored energy, but it's not this story. And we can find the simplest way to find the constitutive equation for our system. Of course, there are different ways to write the constitutive equation, but here I use the simplest one. I use the linear Onzaga relationship and write the equation for the plastic deformation and for these additional parameters. Up to now, it's some additional parameters which should describe our structure evolution. And we keep in mind our previous experiments with this parameter have a bulk mode, and we should find some representation of these defects. This representation was made by Professor Naimak in 1982. He has considered the penny-shaped crack and write the energy of this crack and what most important distribution function for this ensemble. If we have distribution function and geometry and energy of this defect, we can easily write the thermodynamic potential of this system, linear elastic media with defects, with known statistical properties. We can also calculate the additional deformation which can be introduced by these defects, and here you can see the solution of self-constitutive equation in the simplest case. It's not enough to calculate the evolution, it's not enough to describe the statistical loading, And after some attempts, we a little bit changed this ensemble and add some statistical properties in this ensemble. I'm not going into detail, I have no time. But we have concentration of defects as a function of stress amplitude. If we combine these two results, we can obtain evolution of our additional deformation structural parameters, which describe the defect evolution versus stress amplitude. So, it's just a thermodynamical idea. We have very simple equation, and the key point of this equation is how we can describe the thermodynamic potential. We can go to phenomenological level. If we are working in very high cyclic fatigue, I will forget about plastic deformation, ordinary plastic deformation and dissipation caused by dislocation motion, and write only this defect. The equation can be written as a follows, and I have add some non-local effect in this ensemble to be able to describe what I'm going to do. It's possible to explain if we introduce functional derivation of our thermodynamic potential, and after we have quite simple equation, and we should describe this function and try to solve some boundary condition problem. Up to now, nothing interesting, but we try to simulate it in quite simple way. We try to solve ordinary differential equation. We can see the two volumes, one of them located just near the surface, and second one located far from the surface. What is the difference between these volumes? There is only one difference. There is a sample surface, and I have to introduce some mathematical description of the surface. The surface can be sources of defects with positive or negative sign. It means there is a difference in the boundary conditions for these two volumes. Nothing more. I have right description. I have function of free energy. I have non-local effect, and I have surface as a real physical object. That's all what I need to describe why the defect initiation moves to the bulk of the sample. If I write the equation for mean defect density in this and these volumes, I can obtain two practically similar ordinary differential equation, and only one difference is a constant which describes the influence on the surface. If I try to simulate, just to make numerical simulation to find the solution of this equation, for high stress amplitude, I can see practically monotonic, practically constant value of defect density in the bulk and sharp increasing in the surface. I have an influence on the surface. For small stress amplitude, it's completely different. I have stable defect concentration on the surface, on the specimen surface, on the volume located near the surface, and I have sharp increasing inside, but which occur in 10 or maybe more in 10,000 times later. I have considered just three simple physical mechanisms, and each give me very interesting equation, which can be finally, each equation can be rewritten as a function of lifetime, and we have duplex Euler curve which describes the same equation and influence just the constant which describes the specimen surface. It was done a few years ago, but now I'm interested, is it possible to introduce the temperature in this equation and calculate together defect evolution and temperature equation. It is results of Italian group, and we can see the increase of temperature in the end of the sample. I also apply the same equation. I take the equation from defect density, simplify it and write it in cylindrical coordinates. So it's a critical cross-section of the sample, and I will calculate just 1/4 of this area. I write this equation in cylindrical coordinate, add approximation of previous results for this function, and also introduce boundary condition. As I told you, there is a boundary condition which have to be taken into account. And I have taken the energy balance equation from the previous slide, and just rewrite it in the same coordinate system. So I have two equations for defects evolution and for temperature evolution in the cross section. And results, it's also results qualitatively the same, but maybe a little more interesting due to the space pictures. In the beginning, I have to introduce some initial defects in my ensemble, and after, if I have relatively high stress amplitude, I can calculate the temperature evolution, and finally I have one or two defects located just on the specimen surface. It's the same, it's mechanism which I presented before. The surface plays very, very important role. If I use the same equation but just decrease the stress amplitude below some level, I have no influence on the surface, and the sample live during long time, and finally it's appear defects initiation into the bulk surface. And it is what's most interesting things, that size of these defects fully determined by the written differential equation, the size and time of this distribution. So if we know the right defects which play the main role, for example, for definite materials, it's a way to determine the constant and determine the characteristic length and characteristic time in this equation. Up to now, we have only the physical description of these mechanisms. So, and it could be very interesting effect, but I think I have no time. And summing up what has been said, I can say that we have some structural investigation. We have shown that that dilatation appear under very high CIP fatigue. We have shown the decreasing of mechanical properties, and propose some mechanical description of the physical process which can move the defects initiation from specimen surface to the bulk. We combine it with energy balance equation, and we are able to calculate the temperature up to now qualitatively. And this equation opens very interesting explanation of mechanism which lives in the basis of initiation such objects like for example refrigerator. That's all what I wanted to say. I hope it wouldn't be very long. Thank you very much for your attention.